and session 3. So basically, we are on our first day of our physics board examination preparation. And so காலையில் நம்ம பார்த்தோம் electric charges and fields, and then we saw what ray optics, and now we'll enter into moving charges and magnetism. So before that, we'll have to see the portions that's prescribed by CBSE. Yes, so let me just check it once. So yeah, so moving charges and magnetism. First of all, we'll see the concept of magnetic field and Oersted experiment. Okay, I don't know what he did. And then we'll talk about Biot-Savart's law and its applications to any current carrying loop. Ampere's law and its applications to infinitely long straight wire. Okay, straight solenoid, force on a moving charge in uniform magnetic and electric fields, force on current carrying conductor in a uniform magnetic field, force between two parallel current carrying. Okay, I'm just talking about this one. Okay, fine. It's looking weird actually. I'm missing something. No, we have not missed anything. So force on a current carrying conductor in a uniform magnetic field. Okay, force between two parallel current carrying conductors, and we'll define ampere. Torque experienced by a current loop in a uniform magnetic field, current loop as a magnetic dipole and its magnetic dipole moment. Then we'll talk about the galvanometer, its current sensitivity and conversion to its ammeter and voltmeter. Okay, fine. So that's the portion. It seems pretty interesting. So we'll have Ampere's law, Biot-Savart's law, force on a current carrying conductor, force on a moving charge in a uniform magnetic field and electric field. So we'll have certain cases, and then we'll talk about the torque, and then we'll talk about the magnetic dipole moment, and then we'll talk about the conversion factors. So as told earlier, I will be following the old NCERT so that I am not missing out any of the derivations, if at all, if there is any. It's actually not required, but still we'll have to be at the safer side. So let's get started. Moving charges and magnetism. Both electricity and magnetism have been known for more than 2000 years. However, it was only about 200 years ago in 1820 that it was realized that it were intermittently related. During a lecture demonstration in the summer of 1820, the Danish physicist Hans Christian Oersted noticed that a current in a straight wire caused noticeable deflection in a nearby magnetic compass needle. He investigated this phenomenon. He found that the alignment of the needle is tangential to an imaginary circle, which has the straight wire as its center and has its plane perpendicular to the wire. This situation is depicted in figure 4.1a. It is noticeable when the current is large and the needle sufficiently close to the wire so that the Earth's magnetic field may be ignored. Okay, fine, great. So reversing the direction of the current reverses the orientation of the needle. The deflection increases on increasing the current or bringing the needle closer to the wire. Iron fillings sprinkled around the wire arrange themselves in concentric circles with wire as the center. Oersted concluded that moving charges or currents produced a magnetic field in the surrounding space. So basically நமக்கு இது நாள் முன்னாடி வரைக்கும் electricity and magnetism. So basically physics அப்படின்றது it's something historical phenomena occurring in day-to-day life. I mean, like whatever happened historically will be accounted in that particular sequence. We will learn about things. So earlier we had an idea of magnetism and we had an idea of electricity, but now that about 200 years ago we came to know the relation between electricity and magnetism. How is it so? So basically Oersted was a scientist. So basically he noticed that a straight wire was causing a deflection in a magnetic compass needle, and when he tried finding what's actually happening, the needle was actually becoming tangential to certain imaginary circle with the straight wire as the center. Yes, so then he was able to find that when the current is large enough and the needle is sufficiently close enough, the Earth's magnetic field is now ignored at this particular moment. Reversing the current reverses the orientation of the needle, and then we had like the deflection increase when the current increased or the needle is being closer to the wire, the iron filling sprinkled around the wire, and then, yeah, finally, what he concluded was the moving charges produced a magnetic field. Moving charges அப்படின்றது is also known as currents. So therefore electricity is producing a magnetic field அப்படின்ற மாதிரியான basisல we are getting started with this chapter. So following this, there was an intense experimentation. In 1864, the laws obeyed by electricity and magnetism were unified and formulated by James Maxwell, who then realized that light was electromagnetic waves. ஸோ அதாவது இந்த பர்டிகுலர் எக்ஸ்பெரிமெண்ட்டுக்கு பிறகு தேர் வாஸ் அ லாட் ஆஃப் யூனிஃபிகேஷன் அக்கரிங் அண்ட் த லாஸ் ஒபேட் பை எலக்ட்ரிசிட்டி அண்ட் மேக்னட்டிசம் வேர் ஆல் யூனிஃபைட் அண்ட் மேக்ஸ்வெல் அப்படின்ற இந்த பர்டிகுலர் நபர் he realized that light was an electromagnetic waves. So radio waves were discovered by Hertz, produced by J.C. Bose and Maggi Marconi. A remarkable scientific and the technological progress has taken place in the 20th century. This is due to our increased understanding of the electromagnetism and the invention of devices for production, amplification, transmission and detection of electromagnetic waves. ஸோ இதுக்கப்புறம் தான் வந்துட்டு இந்த யூனிஃபிகேஷன் ஆஃப் எலக்ட்ரிசிட்டி அண்ட் மேக்னட்டிசம் எலக்ட்ரிசிட்டி பேஸ் பண்ண லாஸும் மேக்னட்டிசம் பேஸ் பண்ண லாஸ் எல்லாமே வந்துட்டு தேவர் யூனிஃபைட் டுகெதர் அண்ட் ஃபைனலி வி கேம் டு conclusion that light was an electromagnetic waves, and from there on we tried creating electromagnetic waves, we tried creating their production, amplification and transmission, all such things. So as you can see in this particular figure, the magnetic field due to a straight along current carrying conductor. So in the first case scenario it is the current is emerging out of the plane. We'll assume to be the current emerging out of that plane. In that case scenario, we can see the north of the needle is placed to on the right or something left, and at the same instant, if the particular current is reversed, we are observing the needle to be deflected exactly in the opposite sense. So the effect of Earth's magnetic field is actually neglected in this particular point. So in this chapter, we will see how a magnetic field exerts forces on moving charged particles like electrons, protons, and current carrying wires. We shall also learn how currents produce magnetic fields. We shall see how particles can be accelerated to very high energies. So actually that part is deleted. So we shall study how currents and voltages are detected by galvanometer. So yeah, we'll talk about forces, we'll talk about production of a magnetic field due to currents, and then we'll talk about detection of these by a galvanometer. And in subsequent chapter on magnetism, we adopt the following convention. A current or a field emerging out of the plane of a paper is depicted by a dot. A current or a field going into the plane of the paper is depicted by a cross. Okay, fine, great. Now we'll talk about magnetic force, the sources and fields. Before we introduce the concept of magnetic field, we shall recapitulate what we have learned in chapter 1 about the electric field. So we have seen that the interaction between two charges can be considered in two stages. The charge capital Q, the source of the field, produces an electric field E, where E is equal to Q by 4 pi epsilon times R square, the whole R cap, where R cap is a unit vector along the R and field is a vector, okay, it's a vector field. A charge Q interacts with this field and experiences a force given by the charge multiplied by the field value, which is Q by R square. As pointed out in the chapter 1, the field E is not just an artifact but has a physical role. It can convey energy and momentum and is not established instantaneously but takes finite time to propagate. ஸோ அதாவது சாப்டர் 1ல் பொறுத்த வரைக்கும் நம்மளோட எலக்ட்ரிக் ஃபீல்டில் என்ன சொன்னோம், இது இட் ஹேஸ் அ ஃபிசிக்கல் ரோல் அப்படின்ற மாதிரி சொன்னோம். அதாவது இட் கேன் கன்வே எனர்ஜி இன் மொமெண்டம், ஆனால் இட் சேஸ் தட் இட் வில் டேக் சம் டைம் ஃபார் ப்ரொபகேஷன் அப்படின்ற மாதிரியான ஒரு ஆஸ்பெக்டில் வந்துட்டு வி டிஃபைன்ட் எலக்ட்ரிக் ஃபீல்ட். The concept of a field was specially stressed by Faraday and was incorporated by Maxwell in his unification of electricity and magnetism. So basically, the field அப்படின்ற ஒரு மேட்டரே வந்துட்டு Faraday அப்படின்ற ஒரு நபர் தான் வந்துட்டு உருவாக்குறார் when he was trying to capitulate the law for the electrolysis, and it was incorporated by Maxwell. So Maxwell made use of this in electricity and magnetism. So it is really important to know various aspects of what we are learning so that it can be used for unification of various things. So in addition to depending on each point in space, it can also vary with time. Okay, so அதாவது though it can also like it depends on space அப்படின்றத பொறுத்த வரைக்கும், that's how fields are actually defined as, and it turned out that it can also vary with time. So that is, it can be a function of time. So in our discussions in this chapter, we will assume that the fields do not change with time. So in the particular chapter basis, we will not talk about change in time, but we will talk only about the field and its intensity at each point in space. So the field at a particular point can be due to one or more charges. If there are more charges, the fields add vectorially, as we have learned in chapter 1, that this is called the principle of superposition. Once the field is known, the force on a test charge is given by equation 4.2. So what is equation 4.2 is that this F is equal to QE, where QE is the electric field due to the presence of a charge capital Q. Yes. So just as static charges produces an electric field, the currents or moving charges produce a magnetic field. A static charge can produce electric field அப்படின்னா, in addition to an electric field, a moving charge can produce a magnetic field. So that's what we have seen, that moving charges or currents are able to produce magnetic field அப்படின்ற மாதிரி Oersted சொல்லியிருந்தாரு. So it has several basic properties identical to the electric field. So it is defined at each point in space and can in addition depend on time as well. Experimentally, it is found to obey the principle of superposition. The magnetic field has several sources. Is the vector addition of the magnetic field of each individual source. Fine, great. We'll enter into the magnetic field and the Lorentz force. Let us suppose that there is a point charge small q moving with a velocity v and located at r at a given time t. In presence of both the electric field and the magnetic field. Okay, so basically there's a point charge q which is present in place where there are both electric and magnetic field, which varies only with space. So the force on an electric charge q due to both of them will be equal to q times the value of electric field plus q times the value of magnetic field, that multiplied by the velocity, because velocity will be the aspect which will give the sense that the charge is moving, and it will definitely depend, the force will definitely depend on how fast the charge is moving, and that's why we have incorporated the value of velocity as well. So this was first given by Lorentz based on the extensive experiments of Ampere, and it is also called the Lorentz force. So basically Lorentz force is the force of an electric charge q due to both of the electric fields and magnetic fields is this QE plus q times VB, q times V bar cross B bar. So if we look at the interaction with the magnetic field, we find the following. So it depends on the charge, that is fine, but also on the velocity and the magnetic field intensity. So force on a negative charge is opposite to that of the force on a positive charge. Yes, the magnetic force q v bar cross b bar includes a vector product of velocity and magnetic field. The vector product makes the force due to magnetic field vanish if velocity and magnetic field are parallel or anti-parallel. So if in case they both are parallel or anti-parallel, then in that particular scenario, the force due to a magnetic field will be zero, that is null. So the force acts in a sideways direction perpendicular to both velocity and magnetic field. So basically the force acting due to a magnetic field will be perpendicular to both velocity and magnetic field, and that's why we have taken the cross product such that it will be perpendicular to both the vectors. So its direction is given by the screw rule or the right hand rule for the vector cross product. So we'll basically cross from velocity towards b such that the direction which the thumb points gives us the direction of force due to the magnetic field. So the magnetic force is zero if charge is not moving. So if velocity is zero, it is not gonna be, the magnetic force is gonna be null. And even if the the velocity is parallel or anti-parallel towards the magnetic field, then obviously there's not gonna be any presence of magnetic force, and only a moving charge feels the magnetic force. Fine, great. So the expression for the magnetic force helps us to define the unit of magnetic field. The magnetic force expression we will be able to define unit of magnetic field. So if we want to take Q, F and V all to be united in the force equation. So force equation, what we knew was that the force is actually equal to the charge multiplied by the vector cross product of velocity and magnetic field vectors. That is QVB sine theta, where theta is the angle between velocity and magnetic field. So the magnitude of magnetic field B is 1 SI unit, and the force acting on a unit charge moving perpendicular to B with a speed 1 meter per second is 1 Newton. How we are defining magnetic field is that the magnitude of magnetic field B is 1 if the force, when the force acting on a unit charge moving perpendicular, that is sine of theta is becoming 90, sine 90 is becoming 1. So when the force acting on a unit charge is moving perpendicular to the magnetic field with a speed 1 meters per second is 1 Newton. Okay, when the force acting is 1 Newton for a given point charge of 1 coulomb, which is moving at a velocity of 1 meters per second, with that perpendicular to that of the magnetic field, and that particular magnitude will be termed as the magnetic field. So dimensionally we have the dimension of magnetic field is equal to dimension of force divided by dimensions of charge and multiplied by the dimensions of velocity, and the units of B are Newton second per coulomb meter. This unit is called Tesla, named after Nikola Tesla. Tesla is rather a larger unit. A smaller unit called Gauss, which is 1 Gauss is equal to 10 power minus 4 Teslas, is also often used. The Earth's magnetic field is about 3.6 into 10 power minus 5 Teslas. Yes, so that's the intensity of Earth's magnetic field, and we have been listed out with certain magnetic fields. So as you can see, an human nerve fiber has a magnitude of magnetic field of about 10 power minus 10, whereas the surface of a neutron star has a magnetic field of about 10 power 8 Teslas. So force for Newton's Tesla's SI unit, which is Newton second per coulomb meter. Right, moving down, magnetic force on a current carrying conductor. So we can extend the analysis for force due to a magnetic field on a single moving charge to a straight rod carrying conductor. So a particular moving charge, we define the force to be dependent upon the charge, velocity, and the magnetic field density. So we'll consider a rod of uniform cross-sectional area A and length L. We shall assume one kind of mobile carriers as in a conductor. Let the number density of these mobile charge carriers in it be N. So basically I'm considering a cross-sectional area of area A with a length L. Yes, so the length is gonna be L, and yeah, I'm considering that particular type of rod, and let the number density of these mobile charge carriers in it be N. So the number density is going to be N. Then the total number of mobile charge carriers is obviously going to be N multiplied by the volume, and the volume is going to be the area of cross section multiplied by length. For a steady current I in this conducting rod, we may assume that each mobile carrier has an average drift velocity Vd. So அதாவது ஒரு steady current flow நடக்குது அப்படின்னா, which is equal to I, we can assume that each mobile carrier has an average velocity of Vd. So it's gonna be NAL times QVD multiplied by a B. Why is it so? So basically F is equal to Q into velocity multiplied by the B, whatever it is, and okay, in the presence of an external magnetic field. So let's say I have electrons. So if a charge of one electron is considered to be one electron is considered to be Q, and I have N into A into L amount of electrons, which is moving with the drift velocity Vd. So that's the drift velocity of the charge carriers multiplied in a cross product with B, where Q is the value of a charge carrier. Now NQVD is the current density. So as we knew that I don't know, we'll have to derive it actually from the current electricity chapter. Actually, like, it's not that difficult. Yeah, moving on. NQVD is the current density element, and NQEVD, okay, fine, what they are trying to say, which means that the force is actually equal to NQEVD times AL, the whole cross B, which is equal to the current density value multiplied by the area multiplied by the length, the whole cross B, which then the current density multiplied by the volume will give me the current flowing that particular rod multiplied with L into B. Okay, fine. So what they're trying to say, Let me just have some water for a moment. of charge present in a particular start multiplied by q v t plus b. There's actually a lot of small vector. In that last step leading to equation 4.4, we have transferred the vector sign from j to l. J to l, okay. Equation for a straight rod. In this equation, V is the external magnetic field. It is not the field produced by the current carrying rod. So Y has an arbitrary shape. We can conclude the Lorentz force on it can IDLJ, and we'll just integrate it for every strip element of DL. The summation can be converted to an integral in most cases. Permittivity and permeability. In the universal law of gravitation, we say that any two point masses exerts a force on each other which is proportional to the product of the masses and inversely proportional to the square of the distance r between them. We write it as F is equal to g m1 m2 by r square, where g is the universal constant of gravitation. Similarly, in Coulomb's law of electrostatics, we write the force between 2 point charges q1 and q2 separated by distance r as F is equal to k q1 q2 by r square. So k is a constant of proportionality in SI units. K is taken as 1 by 4 by epsilon, where epsilon is the permittivity. And also in magnetism, we take a constant known as mu by 4 pi, where mu is the permeability. Although g, epsilon, and mu arise as a proportionality constant, there is a difference between gravitational force and electromagnetic force. While the gravitational force does not depend on the intervening medium, the electromagnetic force depends on the medium between the two charges of magnets. Hence, while g is a universal constant, epsilon and mu depend on the medium. They have different values for different media. The product epsilon mu turns out to be related to the speed v of the electromagnetic radiation in the medium through epsilon mu is equal to 1 by v square. Electric permittivity epsilon is a physical quantity that describes how an electric field affects and is affected by a medium. It is determined by the ability of a material to polarize in response to an applied field, and thereby to cancel partially the field inside the material. Similarly, magnetic permeability mu is the ability of a substance to acquire magnetization in magnetic field. So, electrical permittivity is the physical quantity that describes I mean, how an electric field affects or get affected by a presence of a medium. And magnetic permeability is the ability of a substance to acquire magnetization in magnetic field. Okay, fine. So, we have certain examples over here. So a straight wire of mass 200 gram and length of 1.5 meters carries a current of 2 ampere. So the current that is being carried is 2, the length is gonna be 1.5 meter and mass is 200 grams, which is 0.2 kg. Suspended mid-air by uniform horizontal magnetic field. What is the magnitude of the magnetic field? So it's basically ILB is mg. B is mg by IL. 0.2 into 9.8, let's say it's a 2 by 2 into 1.5, it's 10 by 15, it's a 2 by 3 Tesla. Note that it would have been sufficient to specify m by L, the mass per unit length of the wire. The Earth's magnetic field is approximately 410 power minus 5 Teslas, and we have ignored it. Okay. So if the magnetic field is parallel to the positive y-axis, okay, which way would the Lorentz force be for an electron and be a proton? So basically, if there is a magnetic field that's parallel to the y-axis, the charged particle is moving along the positive x-axis, okay, which means that it will be for an electron. Oh my god. Okay. Magnetic force will obviously be along the z-axis because the x cross y will obtain a z, positive z. That is fine. Whereas for an electron, it will be along minus z. For positive charge, the force is along plus z. Okay, motion in a magnetic field. We will now consider in great detail the motion of charge moving in a magnetic field. Okay, so we have learned in mechanics, see the class 12 book, chapter 6, that a force on a particle does work if the force has a component along the direction of motion of the particle. In the case of a charge in a magnetic field, the magnetic field is perpendicular to the velocity of particle. So no work is done and no change in magnitude of the velocity is produced. That is, though the direction in momentum may be changed, nonetheless the velocity cannot be changed. So it can be said that there will be a net acceleration, but the net acceleration means that there is a direct change in direction of the momentum. So notice that this is unlike the force due to an electric field QE, which can have a component parallel to the motion and thus can transfer in energy in addition to the momentum as well. So basically, this guy cannot do any work, which means that there will not be any amount of additional momentum due to the presence of a magnetic field or magnetic force. Yes, so we shall consider motion of a charged particle in a uniform magnetic field. First, consider the case of V perpendicular to B. Okay, V perpendicular to B, that is the velocity perpendicular to the magnetic field. So the perpendicular force QV cross B acts as a centripetal force and produces a circular motion perpendicular to the magnetic field, and the particle will describe a circle if V and B are perpendicular to each other. So first case is that I'm having a wholly magnetic field in which the velocity is exactly perpendicular to the magnetic field vector, which means that, yeah, so if velocity has a component along B, this component remains unchanged as the motion along the magnetic field will not be affected. Okay. First consider the case of V perpendicular to B. The perpendicular force QV bar cross B bar acts as a centripetal force and produces a circular motion perpendicular to the magnetic field. The particle will describe a circle if V and B are perpendicular to each other. Okay, fine, great. So the velocity has a component along B. This component remains unchanged as the motion along the magnetic field will not be affected by the magnetic field. The motion in a plane perpendicular to the magnetic field is, as before, a circular one, thereby producing a helical motion. So let's say the velocity is making certain angle with the magnetic field. So in that such case scenarios, the perpendicular vector, the V perpendicular will be contributing for its motion in a circle, and simultaneously we will be having parallel vector of velocity, that is V parallel along the magnetic field, which will make it move in a circular motion and in a linear way simultaneously, which will lead to the formation of a helical surface, helical path. That's a helical motion. So you have learnt in earlier classes that if r is the radius of the circular path, then the force acting is mv square by r, which is actually equal to qvb. When I'm equating these two factors, then the radius is going to be equal to mv by qb. So the radius described will be equal to mass of the charge carrier multiplied by velocity of the charge carrier divided by the charge of the charge carrier and the external magnetic field. Basically, if we have the q by m value, it's going to be sufficient. And for the radius of the circle described by the charged particle, larger the momentum, larger is the radius. Okay, so that is, as we can see, since the radius is directly proportional to the momentum factor, hence larger the momentum, larger is the radius and bigger is the circle. If omega is the angular frequency, and since we knew that v is equal to r omega, which means that v by r is equal to omega, omega is equal to 2 pi v, okay, which is equal to qb by m. qb by 2 pi nu, okay, fine, whatever it is. So which is independent of the velocity or energy. So that is the angular frequency about which this particular guy is revolving or whatever is gonna be independent of whatever the velocity or energy. So here nu is the frequency of rotation. The independence of the frequency from energy has important application in the design of a cyclotron. So as you can see, in the particular case scenario where there is only the presence of solely a presence of magnetic field in that particular place, there is a moment of a charge in a radius equal to mv by qb, and as the momentum increases, the radius increases as well. And now that we knew that v is equal to r omega and v is equal to mv by qb times, that's r times omega, so omega equals qb by m. So as we can see over here, the angular frequency part, which is equal to 2 pi times the frequency part itself, is actually independent. The frequency is independent of what the guy is moving with, what velocity the guy is moving with. That is the amount of kinetic energy, it is moving it. So basically it is independent of what is the amount of energy that is being attained by that particular particle. So the time taken for one revolution 2t is equal to 2 pi by omega, which is going to be equal to 1 by nu, and nu turns out to be uh, 2 pi m v by qb. 2 pi m v by qb will be the, okay, so 2 pi m by qb will be my time period, and that multiplied by the velocity will give me the amount of distance that it has followed. And for one time period revolution, the amount of distance it has traveled is what we call as the pitch. So the radius of the circular component of motion is called the radius of the helix. So moving down, what is the radius of the path of an electron? So we have been given with the mass and the charge moving at a speed. So the speed is given and the magnetic field vector is given. And what is its frequency? Calculate its energy in kilo electrovolt. Okay, fine. So let's say R is equal to mv by qb. Mass of the electron is 9 into 10 power minus 31, and velocity is 3 into 10 power 7, and charge of the electron is going to be 1.6 into 10 power minus 19, and magnetic field is 6 into 10 power minus 4. So this ellame is present over here, and 9 3s are 27, 10 power minus 31 into 10 power 7 is going to be 10 power minus 24 divided by 1.6 into 6 into 10 power minus 23. Oh my god. Okay, 27 by 9.6 into 10 power minus 1. It's basically 27 by 96, something like that. Is it so? Okay, it turns out that the value is equal to 26 centimeter approximately. Great. So which means that the frequency is actually 2 pi v is equal to omega, and we knew that v is equal to r omega, v by r is equal to omega qb by m, 2 qb by m. So nu is equal to qb by 2 pi m, I think. Is it so? That is 2 megahertz, it seems. So the energy is going to be equal to half mv square, whatever the velocity is going to be. So half into 9 into 10 power minus 31 into 9 into 10 power 14, and that's going to be 4 into 10 power minus 16 joules. That divided by 1.6 into 10 power minus 19 will give me 4 divided by 1.6 will be a 1 divided by 4, something like 2.5 kilo electron volt. So that's it. That's the substitution of whatever the formulae we have learned as far till now. So in polar regions like Alaska and northern Canada, a splendid display of colors is seen in the sky. The appearance of the dancing green-pink lights is fascinating and equally puzzling. An explanation of this natural phenomena is now found in physics in terms of what we have studied here. Consider a charged particle of mass m and charge q entering a region of magnetic field B with an initial velocity v. Let this velocity have a component Vp parallel to the magnetic field and Vn normal perpendicular to whatever it is. There is no force on a charged particle in direction of the field. Hence, the particle continues to travel with the velocity Vp parallel to the field itself. The normal component of the particle will result in a Lorentz force, which is perpendicular to both Vn and B. As seen in figure 4.3.1, the particle thus has a tendency to perform a circular motion in a plane perpendicular to the magnetic field. When this is coupled with the velocity parallel, then we'll obtain a helical trajectory as shown in figure A here. Even if the field line bends, the helical moving particle is trapped and guided to move around the field line. Okay. Since the Lorentz force is normal to the velocity of each point, the field does no work on the particle and the magnitude of velocity remains the same. So during a solar flare, a large number of electrons and protons are ejected from the sun. Some of them get trapped in the Earth's magnetic field and move in helical paths along the field lines. Okay, so the field lines come closer to each other near the magnetic poles. So as we have seen in the figure B, hence the density of the charges increases near the poles. These charges, these particles collide with the atoms and molecules. Excited oxygen atom emit green light and excited nitrogen atoms emit pink light. This phenomena is called the aurora borealis in physics. Okay. So motion in combined electric and magnetic fields. So as we have seen the motion in pure magnetic fields, now we'll encounter motion in combined electric and magnetic fields. So I don't think we have cyclotron. So that's not going to be a big matter of concern. Then we'll directly enter into the magnetic field due to current element of Boyd-Savitz's law. Okay. So first we'll see this velocity selector. So you know that a charge q moving with a velocity v in presence of both electric and magnetic fields experiences a force that is F is equal to q times E plus v bar cross b bar, that is Fe plus Fb. We shall consider the simple case in which the electric and magnetic fields are perpendicular to each other and also perpendicular to the velocity of the particle. So we will have a simple case scenario in which the electric and magnetic field are perpendicular and it is also perpendicular to the whatever the velocity it was moving with. So let's say the electric field is in the particular y direction, positive y direction, the magnetic field is in the particular positive z direction, the velocity is in positive x direction. So Fe is equal to QE is acting along the y direction and Fb is QV bar cross B bar. So that is I cross K. I think it will be resulting in a minus J. So we'll have the Fb in the negative J direction, that is minus QV. So it turns out that the whole of the force will be acting in the along the y direction, either in the positive sense or the negative sense, depending upon the values of electric field and the values of QB. So if electric field value is turning out to be greater than QB, then the force will be acting along the positive y direction. And similarly, if the product of magnetic field and the charge is turning out to be greater than that of the electric field intensity, then the force will be acting in a negative direction. Thus, the electric and magnetic forces are in opposite directions as shown in the figure. Suppose we adjust the values of electric field and magnetic field such that magnitude of the two forces are equal. So it turns out that magnitude of both the forces are being equal, which means that in that particular case, okay, so then the total force on the charge is 0. Why? So okay, and the charge will move in the fields undeflected. So what they are trying to say is that we'll adjust the values of E and B such that magnitude of both the forces, that is QE is equal to QVB and V is equal to E by B அப்படின்ற particular type scenario. It turns out that the net force acting on the particular particle will be equal to 0, which means that there will not be any kind of deflection occurring. It will move undeflected அப்படின்ற சொல்றாங்க. So this condition can be used to select charged particles for a particular velocity out of a beam containing charges moving with different speeds. So used to select charged particles of a particular velocity out of a beam containing charges moving with different speeds. Okay, so basically irrespective of their charge and mass, it can be useful in selecting certain particles. Okay, so the crossed electric field and magnetic fields therefore serve as a velocity selector. Only particles with a speed E by B pass undeflected through the region of crossed fields. So this method was employed by J.J. Thomson to measure the charge to the mass ratio, that is E by M ratio. The principle is also employed in mass spectrometer, a device that separates the charged particles. So basically this particular adjustment of electric field and the magnetic field will be useful in separating the charged particles. The one which is moving undeflected will be separated out, that okay, from the ones which are not deflected, whatever it is. So we have certain accelerators in India, charge accelerators. I don't think we'll need to note this now. Okay, yes, so moving down. Yes, we'll talk about the magnetic field due to a current element, that's the Boyd-Savitz's law. So all the magnetic fields that we know are due to the currents and due to intrinsic magnetic moments of particles. Here we shall study the relation between current and the magnetic field it produces. So basically, whatever the currents we knew, or I mean whatever the magnetic fields we knew are all due to the currents, that is due to the magnetic moving charges. And now we'll study about the relation between the current and magnetic field it is producing, and that's what Boyd-Savart's law is all about. So basically the magnetic field, the differential magnetic field produced due to a differential current element dl of a conductor, let's say, which is carrying a current I, is directly proportional to the product of IDL, and it is also proportional to the distance from which we are obtaining the particular expression. And it turns out that it is okay, wait a minute, it is okay, I'm sorry, it's actually inversely proportional to the distance square and directly proportional to the current and the current element total length dl. So which means that the differential magnetic field acting upon the particular guy is directly proportional to the ideal vector cross r bar by r cube, which is, and the proportionality constant is mu naught by 4 pi, where it's a constant of proportionality when this particular thing is happening in a vacuum medium. So magnitude of the field is turning out to be mu naught by 4 pi times IDL sine theta by r square. So that's the differential magnetic field that's been produced, where we have used the property of cross product. So cross product in the sense basically IDL r sine theta by r cube, and r factor gets cancelled over here. So IDL bar by r square times sine theta. I think from magnitude only we will be actually able to derive the value of the vector property, that is IDL bar cross r bar by r cube. So where we have used the property of cross product, and the equation 4.11a constitutes our basic equation for the magnetic field. The proportionality constant is what the mu naught by 4 pi is actually 10 power minus 7 Tesla meter per ampere, where mu naught is called the permeability. Mu naught is permeability in vacuum of free space. Okay, so the Boyd-Savart's law for the magnetic field has certain similarities as well as differences with Coulomb's law for the electrostatic field. So now that we have obtained two laws in which we will be obtaining the fields as well, field and forces or whatever. So it is important to have certain comparative studies so that it will be easier for us to remember. So both are long range, since both depend inversely on the square of distance from the source to the point of interest. So இது ரெண்டுமே லாங் ரேஞ்சு. ஏன் அப்படின்னா it is actually inversely proportional to square of distance. The principle of superposition apply to both the fields. Note that the magnetic field is linear in the source ideal, just as the electrostatic field is linear in its source electric charge. Okay, the electrostatic field is produced by a scalar source, namely the electric charge. The magnetic field is produced by a vector source known as the ideal. Okay, the electrostatic field is along the displacement vector joining the source and the field point. The magnetic field is perpendicular to the plane containing the displacement vector r and the current element ideal. So basically நம்ம என்ன சொல்றோம், இந்த ரெண்டு கைஸ்மே வந்துட்டு they are inversely proportional to the distance of square, and electrostatic field is produced by a scalar அப்படின்னா, scalar source அப்படின்னா, that's an electric charge அப்படின்னா, this guy is produced by a vector source known as the ideal, and electric field is along the displacement vector joining the source and field point. Magnetic field is perpendicular to the plane containing the displacement vector. So that it is basically acting perpendicular to the direction of motion of the particular particle, whereas the electric field will be actually acting in the direction of the particle itself. So there is an angle dependence in the Boyd-Savart's law, which is not present in the electrostatic case. Okay, so electrostatic case of we do not have anything like an angle dependence, whereas in case of Boyd-Savart's law we have the angle dependence of sine theta. Okay. There is an angle dependence in the Boyd-Savart law which is not present in the electrostatic case. Okay, fine. And the magnetic field at any point in the direction of dl is 0. So as we have seen that the direction dependence is about sine theta, which means that we'll obviously be having no force because the angle dependence is 0, which means along the vector, along the direction, the force is gonna be 0. Along this line theta 0, sin theta 0, then obviously the magnitude of magnetic field also turns out to be 0. So there is an interesting relation between epsilon naught, the permittivity of free space, and mu naught, the permeability of free space. So basically when I'm multiplying these two guys, so mu naught times epsilon naught is actually equal to 4. I can basically have a 4 pi epsilon naught times mu naught by 4 pi, and we knew that the value of 4 pi epsilon naught is 9 into 10 power 9, and this guy's value is 10 power minus 7. Sorry, it's a 1 by 10 power 9. Okay, whatever. Okay, so actually k's value is k is equal to 1 by 4 pi epsilon naught, which is equal to 1 by 9 into 10 power 9. And since we have the value of 4 pi epsilon naught, it's actually 9 into 10 power 9, that multiplied by a 10 power minus 7 factor in the denominator. So it turns out that we are having a 1 into 3 power 1 by 3 into 10 power 8 the whole square. And since we have seen the value of speed of light to be equal to that value in most cases, so it's the product of permeability of free space to that of the permittivity of free space is 1 by the square of speed of light. So we will discuss this connection further in chapter 8 on the electromagnetic waves. Since the speed of light in vacuum is constant, the product mu naught times epsilon naught is fixed in magnitude. Choosing the value of either epsilon naught or mu naught fixes the value of the other. In SI units, mu naught is fixed to be equal to 4 pi into 10 power minus 7 mu. Okay, so whatever the value of mu naught and epsilon naught, if we knew the value of mu, it's gonna be then the value of epsilon naught is obviously gonna be kept constant, since the product is actually equal to a constant value. So according to SI units, we'll fix the value of permeability to be equal to 4 pi into 10 power minus 7 அப்படின்ற மாதிரி சொல்றாங்க. So moving on, an element delta L is equal to delta x multiplied by I cap is placed at the origin and carries a large current I. So let's say I have a current that is being flowing, that's about 10 amperes. Yes. So what is the magnetic field on the y axis at a distance of 0.5 meter? Holy, god damn it. They're asking the magnetic field. So according to Boyd-Savart's law, it is actually equal to I dl sin theta by mu naught by 4 pi times I dl sin theta by r square. And what we knew is that delta x value, okay, y axis அப்படினா it is obviously going to be perpendicular to the current element vector, which means that the sin theta factor is taken care of, it is taken to be 1, and the distance is taken to be 0.5, which means that 0.5 meters, which is actually 25 into 10 whose square is actually equal to 25 into 10 power minus 2. And we knew that mu naught by 4 pi is actually 10 power minus 7. The amount of current flowing in this particular is 10, and the differential element length is actually equal to 10 power minus 2 meters. I'm converting into SI units because they have given it as in centimeters, and that divided by 25 into 10 power minus 2. Yes, 10 power minus 2 factor gets cancelled. That's a 2 by 5 into 10 power minus 7. That's a 4 by 10 into 10 power minus 7. That's actually 4 into 10 power minus 8 Teslas. So that's the amount of field, that's the magnitude of field at that particular point on y-axis. So the direction of the field is in the positive z direction. So basically when I'm, why is it so? Basically we'll have to calculate it into the respect to v bar cross b bar or whatever that is. This is since because when I'm calculating dl bar cross r bar and the l bar cross r bar odia cross product. So L bar is along positive I, and okay fine, which means that I will have a positive z. So positive I cap with the cross product with the positive j cap will give me a positive k cap, and yeah. So we remind you of the following cyclic property of the cross products, that is I bar cross j bar is equal to k cap, I cap j cap plus k cap is equal to I cap, k cap I cap is equal to j cap. So now that the field is small in magnitude, okay. So in the next section we shall use the Boyd-Savart's law to calculate the magnetic field into a circular loop. Okay, now that we are gonna enter into circular loop, so the evolution entails summing up the effect of infinitesimal current elements. So namak enna theriyum, for a differential the differential field produced due to current element of a differential L length is ideal sin theta by r square. So mu naught by 4 pi times ideal sin theta by r square. Now that we'll have to sum it up for all dl elements. So if I'm taking into consideration of that dl elements, let's say I have a circular loop, and if I'm trying to calculate the value of electric field at at a point on the axis from at a distance of x, let's say, and let's say the circular loop has a radius of capital R, in which current is flowing, I amount of current is flowing, and we have different, I mean the dl lengths are basically perpendicular to the okay, dl lengths are actually perpendicular to r, that is the distance from the particular point of interest, which means that the sin theta factor is taken care of. And then what else do we have? So when I'm trying to calculate this, there will be, let's say there will be a net electric field obtained, and there will be net electric field obtained in which the perpendicular component vectors are all cancelled out, since they are all equal in magnitude and opposite to each other, and only the parallel components, that is the cos theta components, I think, or will be taken into considerations. Yes, so which means that it's the differential I mean this whatever magnetic field produced will be equal to mu naught by 4 pi times IDL by x square plus r square, and the root of x square plus r square the whole square, which means that it's a x square plus r square factor, and we'll consider only the cos theta components, and cos theta turns out to be oh my god, cos theta, so what's the value of cos theta? I'm sorry, my mistake. Yeah, it turns out to be r by, that is r is the value of, yes, that divided by x square plus r square whole root. So now I will multiply these two factors, mu naught by 4 pi times IDL by x square plus r square times r by x square plus r square the whole power 1 by 2, and it turns out that it's equal to mu naught by 4 pi times IDL by IDL r by x square plus r square the whole power 3 by 2. Okay, fine, great. Okay, so the summation of the elements of dl, so which means that basically the dl value will be turn out to be equal to 2 pi r square. Yes, so which means that I will take mu naught by 4 pi times I into 2 pi r the whole times r divided by x square plus capital R square the whole power 3 by 2, and 2 pi factor gets cancelled over here, and what I'll obtain with mu naught I r square by 2 times x square plus r square the whole power 3 by 2, and if I consider x to be far, I mean at x is equal to 0, it turns out that I will obtain the value to be equal to mu naught I r I by 2r, mu naught I by 2r, that is at the center the value of the magnetic field due to a circular loop is mu naught by 2r times I, mu naught I by 2r, whatever. So the magnetic field lines due to circular wire form closed loops as shown. So as you can see, if there is a current flowing in the particular wire in this, let's say in the anti-clockwise sense as they have shown in this particular diagram, so which means that there will be closed loops of magnetic field that's occurring. Yes, okay. So the right hand thumb rule gives the direction of the magnetic field. So if it is moving in anti-clockwise sense in this particular diagram, then accordingly the magnetic field is actually directed, let's say it's directed outside or whatever, from the lower to the upper part. Okay, so what they're trying to say is the upper side of the loop may be thought as the north pole. Why is it so? Because the fields are originating. The field lines are originating from that particular part of the loop, which means that it can be considered as a north pole, and simultaneously the one the lower part can be considered to be as the south pole, as the field lines are entering through that particular part. Moving down, a straight wire carrying a current of 12 ampere is bent into a semicircular arc of radius 2 centimeter. Okay, so basically I'm obtaining a semicircular arc which is having a radius of about 2 centimeters. Consider the magnetic field B at the center of the arc. Okay, so in what is the magnetic field due to the straight segments? So basically at the center along the direction, so ideal cross R, I think since the theta value is 0, which means that the straight segments do not consider, I mean contribute for any amount of magnetic field. So in what way the contribution to B from the semicircle differs from that of a circular loop, and in what way does it resemble? Okay, so for all segments of the semicircular arc, dl bar cross r are all parallel to each other. So dl bar cross r are into the plane of the paper. In case of the first one, all such contributions add up in magnitude. Hence, the direction of magnetic field for semicircular arc is given by the right hand rule, and magnitude is half that of the square circular loop. That is, thus P is actually equal to 1 by 9 into 10 power minus 4 Teslas. Okay, why is it so? dl bar cross r எல்லாமே parallel இருக்குன்ற காரணத்தினால everything will be added up to give half the contribution, because we are having only a semicircular loops, and in case of dl calculation it will taken only, will be considering only half the amount of loop. Okay, so what is the difference is that they are opposite in directions in case of A and B. Consider a tightly wound 100-ton coil of radius 10 centimeter. Okay, fine. Carrying a current of 1 ampere. What is the magnitude of the magnetic field at the center of the coil? Uh, 100 tons, which means that we'll have to multiply it 100 times with whatever the contributions that we are obtaining. So since we know that it's a mu naught I by 2r, and since we have 100 tons, that's multiplied with 100. So mu naught's value is 4 pi into 10 power minus 7. Value of current is 1 ampere. 2 times the radius. Radius is going to be 10 into 10 power, whatever, 10 power minus 1. Yeah, 2 pi into 10 power minus 4. That's 6.28 into 10 power minus 4 Teslas. Going down, we have Ampere's circuital law. So there is an alternative and appealing way in which the Boyd-Savart law may be expressed. Ampere's circuital law considers an open surface with a boundary, figure 4.14. The surface has current passing through it. We consider the boundary to be made up of a number of small line segments. Okay, fine, great. Consider one such element of length dl. We take the value of the tangential component of the magnetic field at this element and multiply it by a length of. Okay, wait a minute. Let me just have a small break.